Hello friends, continuing with the topic of Ohm's law, today we take up fifth part, effect of temperature on resistance. I repeat, the topic is effect of temperature on resistance. Now first term that we have to understand is temperature coefficient of resistance of a conductor. What we have to understand? Temperature coefficient of resistance of a conductor. Now first take up its definition. What is the definition? Change in resistance per unit initial resistance per unit change in temperature is defined as temperature coefficient of resistance of a conductor. I repeat, change in resistance per unit initial resistance per unit change in temperature is defined as temperature coefficient of resistance of a conductor. Second, mathematical expression. If Ri be the initial resistance of a conductor at initial temperature Ti and Rf be the final resistance of the conductor at final temperature Tf, then temperature coefficient of resistance alpha can be expressed according to definition as alpha is equal to R final minus R initial divided by R initial into T final minus T initial. I repeat, if Ri be the initial resistance of a conductor at initial temperature Ti and Rf be the final resistance of the conductor at final temperature Tf, then temperature coefficient of resistance alpha can be expressed according to definition as alpha is equal to Rf minus Ri divided by Ri into Tf minus Ti. Now third, SI unit, Kelvin inverse, that is per Kelvin is the SI unit of temperature coefficient of resistance. Now we have to understand the term positive temperature coefficient of resistance after defining temperature coefficient of resistance. Now first, definition of positive temperature coefficient of resistance. How we define it? Increase in resistance per unit initial resistance per degree rise in temperature of a conductor is defined as positive temperature coefficient of resistance. I repeat, increase in resistance per unit initial resistance per degree rise in temperature of a conductor is defined as positive temperature coefficient of resistance, or decrease in resistance per unit initial resistance per degree fall in temperature of the conductor is defined as positive temperature coefficient of resistance. I repeat, decrease in resistance per unit initial resistance per degree fall in temperature of the conductor is also defined as positive temperature coefficient of resistance. For example, alpha is positive for metals and alloys. Second, RT relation. If R0 be the resistance at 0 Kelvin and RT be the resistance at T Kelvin, then temperature coefficient of resistance alpha is equal to RT minus R0 divided by R0 into T minus 0, or it is equal to RT minus R0 divided by R0 into T, or alpha R0 T is equal to RT minus R0. Rearranging, we have RT is equal to R0 plus alpha R0 T, and finally we have RT is equal to R0 into 1 plus alpha T. So this is how we get the RT relation, that is relation between resistance and temperature. The third is RT graph. RT graph is as shown. This is R0, the intercept on y-axis, and this is RT, and this is temperature axis. The fourth, alternative definition of temperature coefficient of resistance. Now, slope of RT graph is also defined as temperature coefficient of resistance of a conductor. I repeat, slope of RT graph is also defined as temperature coefficient of resistance of conductor. More the slope, more is alpha. Lesser the slope, less is alpha. Now, RT graph for metals and alloys have been shown here separately. So, this is RT graph for metals, this is RT graph for alloys. Now, slope of RT graph for metals is more than the slope of RT graph of alloys. Thus, metals have more alpha than alloys. That is why alloy wires like manganese and Constantan are used in standardizing equipments like meter bridge and potentiometer. Assignment 3.1 continued. Question number 26. The RT graph of two materials are as shown. Which of the two represents metals? Number 2, alloys. So you have to look at the graph and tell us which graph represents metals and which graph represents alloys. Question number 27. Why alloy wires are used in meter bridge and potentiometer? Fifth, ρ-T relation. Now, since resistance of a conductor at any temperature T is given by the expression RT is equal to R0 into 1 plus alpha T, and also RT is equal to ρ-T into L by A. Therefore, we can write ρ-T into L by A is equal to RC into 1 plus alpha T, or we can write R0 as ρ0 L by A. So, here we get ρ-T into L by A is equal to ρ0 into L by A into 1 plus alpha T. We have replaced R0 by ρ0 into L by A. Now, ρ-T is equal to ρ0 into 1 plus alpha T, because L by A cancels. Now, ρ-T graph. If we draw ρ-T graph, it comes out to be as shown in diagram. Now, ρ-T relation in terms of energy gap Eg is given by the expression ρ-T is equal to ρ0 into e raised to power minus Eg by kBT. This is how ρ-T relation is given in terms of energy gap. So far, we have learnt about positive temperature coefficient of resistance, and now we come to negative temperature coefficient of resistance. The process and steps are similar as in positive temperature coefficient of resistance. So, first is definition. Increase in resistance per unit initial resistance per degree fall in temperature of a conductor is defined as negative temperature coefficient of resistance, or decrease in resistance per unit initial resistance per degree rise in temperature of conductor is also defined as negative temperature coefficient of resistance. For example, alpha is negative for semiconductors, insulators, and electrolytes. Second, RT relation. If R0 be the resistance at 0 Kelvin and RT be the resistance at T Kelvin, then temperature coefficient of resistance minus alpha, minus for negative, alpha for temperature coefficient. So we write minus alpha is equal to RT minus R0 divided by R0 into T minus 0. RT is equal to RT minus R0 divided by R0 into T. On cross multiplying we get minus alpha R0T is equal to RT minus R0, and then rearranging we get RT equal to R0 into 1 minus alpha T. We take out R0 common here, and then finally we have RT is equal to R0 into 1 minus alpha T. So this is the required relation, RT relation, so far as negative temperature coefficient of resistance is concerned. Now RT graph, third point we take up, RT graph. RT graph is as shown. So this is R0, the intercept on y-axis, is RT on y-axis and T along x-axis. So this is how we get the graph. If we plot graph, it is a straight line as shown, because RT is equal to R0 into 1 minus alpha T is the equation of a straight line. Okay. Fourth, rho T relation. Rho T relation, so far as the negative temperature coefficient of resistance is concerned, it is given by the expression rho T is equal to rho 0 into 1 minus alpha T. This relation has been derived from the original relation of resistance RT is equal to R0 into 1 minus alpha T. In this equation we put the value of RT is equal to rho 0 L. In this relation we substitute the value of RT equal to rho T into L by A, and for 0 we write rho 0 L by A. So when we substitute the values in the relation RT is equal to R0 into 1 minus alpha T, L by A and L by A cancel on both sides, and we are left with the relation rho T is equal to rho 0 into 1 minus alpha T. I have left it to you because already we have derived the relation rho T is equal to rho 0 into 1 plus alpha T in positive temperature coefficient of resistance. So you derive yourself. So the final relation is rho T is equal to rho 0 into 1 minus alpha T. Now fifth, rho T graph. Rho T graph is as shown. Sixth, rho T relation in terms of energy gap. The rho T relation in terms of energy gap is given by the expression rho T is equal to rho 0 into e raised to power Eg by kBT. Now if you compare with positive temperature coefficient of resistance, there we had minus Eg by kBT, and for negative temperature coefficient of resistance we have Eg by kBT. So this is the only difference between the expressions, so you can remember it. Now seventh, alternative formula for temperature coefficient of resistance when R0 is unknown. If R0 be the resistance of a conductor at temperature T0 and R1 be the resistance at temperature T1, then R1 can be expressed as R1 equal to R0 into 1 plus alpha T1. Let us mark it as equation 1. And if R2 be the resistance at temperature T2, then R2 can be expressed as R2 is equal to R0 into 1 plus alpha T2. Let us mark it as equation 2. Now dividing equation 1 by equation 2, we get R1 by R2 is equal to R0 into 1 plus alpha T1 divided by R0 into 1 plus alpha T2. So R0 cancels. Then we are left with 1 plus alpha T1 divided by 1 plus alpha T2. And on cross multiplying we get R1 into 1 plus alpha T2 is equal to R2 into 1 plus alpha T1. Now on opening the bracket we get R1 plus R1 alpha T2 is equal to R2 plus R2 alpha T1, or R1 alpha T2 minus R2 alpha T1 is equal to R2 minus R1. Finally, we have alpha is equal to R2 minus R1 divided by R1 T2 minus R2 T1. Let us mark it as equation 3. Now, equation 3 gives an alternative formula for alpha, temperature coefficient of resistance, whether positive or negative. If alpha is positive, the expression is as shown. If alpha is negative, then in place of alpha we will have minus alpha. Assignment 3.1 continued. Question number 28. A silver wire has a resistance of 2.1 ohm at 27.5 degrees Celsius and a resistance of 2.7 ohm at 100 degrees Celsius. Determine the temperature coefficient of silver. Question number 29. Calculate the temperature at which the resistance of a conductor becomes 20% more than its resistance at 27 degrees Celsius. The value of temperature coefficient of resistance of the conductor is 2.0 into 10 raised to power minus 4 per Kelvin. Okay, next time we'll take up part 6, that is superconductivity. Till then, goodbye.